right, we'll go on and we'll finish up definite integrals. This is a useful theorem. You've seen the first part of this before. It's just the definition of a definite integral, and that is that the definite integral on some interval a to b is equal to the limit, as n approaches infinity, of the sum of the areas of all the rectangles. And remember that delta x is b minus a over n. That gives you the width of each rectangle. And any particular x value you can find by taking the beginning of the interval, that is a, whatever that value is, and adding I, so whichever rectangle you're on, times the width of a rectangle. And that will get you the x value where you are at the current moment. So we're going to do just a little exercise. We're going to express the limit of a sum as an integral. So we have, you can see in the blue there, the limit as x approaches infinity of this function, the summation as I equals 1 to n, and then the function times delta x. So let's take apart what we've got there in our summation. Remember that delta x is the width of the rectangle, so all the widths are the same. Once you figure out what the width is, you stick with that single width. And then the function itself at any particular point, f of x sub I, is 2 times the square root of I plus x sub I tan of x sub I. So that's what we have to work with, and our interval is from 0 to 2 pi. So now we want to convert this. So there's our interval. We want to convert this, just simply convert it back into integral form. So we want to use a definite integral. So our definite integral, we have our upper and lower limits. So the lower is 0, the upper is 2 pi. Our function, f of x, 2 square root of x plus x tan of x. And then dx represents our delta x. Let's take a look at the handy summation formulas. You've seen most of these before, and there's actually 3 of these that we're going to be using in the next example. So notice this one that I've got the arrow pointing at. It says that if you have the sum or difference of 2 functions or 2 terms, you can actually separate them into 2 different summations, and that comes in handy. We will also be using the summation from I equals 1 to n of a constant. So notice it's just the constant times n. And then the third one we'll be using is this one where you add up the first n squares of numbers. All right, so let's look at this particular problem. Now, I'm not going to work it all out here on this slide. I have attached the worked example back in Blackboard, so you can click on it and get the whole worked example. But let's get it started here. So first of all, we need to know delta x. We need to know the width of each rectangle. And we have that handy dandy formula. Let's take the width of our interval, 2 minus 0 over n. So the width of each rectangle is 2 over n. And each particular x sub I, how do we get that? Well, according to our formula, we take our lower boundary, which in this case is 0, and we add I times the width of each rectangle. So simplifying, we get 2i over n. Now we're going to use that limit definition and replace f of x sub I with the actual function, which is x squared plus 1. So remember, each particular x is 2i over n. We have to square that, so 2i over n, that quantity squared, plus 1, that's our function, times dx. Remember, dx is the width of each rectangle, delta x. So that's 2 over n. Now, spoiler, first of all, see if you can work it out using the 3 rules formulas that I highlighted in the previous slide, and you should get an answer of 14/3. So spend a little time, see if you can get it, and then go back to Blackboard in where you found the link for this video, and right underneath it you'll see another link, and that will have the worked example. One more thing to take a look at, the midpoint rule. The midpoint rule is just a special rule that says, what if you want to line up your rectangles so that the midpoint of the rectangle is where you find the height of the rectangle? And there's that special notation x sub I with a bar over it, and that says you're using the midpoint. So just like the other theorem that we saw, first we're always going to have to get the width of a rectangle, so we need to know the interval of the curve that we're interested in. So the upper and lower bounds, b minus a over n, will give us the width. That's our delta x. And then x sub I with that bar over it says we're taking the midpoint of a rectangle. So basically you're going to average the previous x and the next x and go to the middle of it to get the midpoint. So let's put that into play here. We want to use the midpoint rule, and now we're given a specific n is equal to 5. So we have this curve x squared, and I've drawn the graph there for you, and it's a good idea when you have some of these, if there isn't a graph given, just to go graph it in Desmos or whatever you use. So n is equal to 5. So the first thing we want to do is find the width of each of those rectangles. And we have an interval from 0 to 2, so that's a width of 2, with 5 rectangles. So each rectangle measures 2/5. So that's the width. And then we want the midpoint. So let's just start with the first one. X sub 1 is 2/5. Remember, x sub 0 is your lower boundary. So x sub 0 is 0. X sub 1, since the width of a rectangle is 2/5, would be 2/5 over from the lower boundary. And so then to find what your midpoint is for the first rectangle, you're going to add x sub 0 plus x sub 1. Remember, x sub 0 was 0 because that's where our interval starts, plus x sub 1, which is 2/5. Take half of that, you get 1/5. So 1/5 is the middle of the first rectangle. If we keep on going, we have x sub 2 is equal to 4/5, and x bar sub 2, so the midpoint between x1 and x2, is 3/5. And that's just from using the formula. So now let's replace everything in our summation. We're going from 1 to 5 because we have 5 rectangles, and we're just going to write everything out the long way. We have delta x, which is 2/5, times, and now we have x squared. So x sub 1 is 1/5 squared, x sub 2, 3/5 squared, and so on. You're going to keep going until you get up to all 5 rectangles, and then you're going to crunch that number to get your answer.